Introduction. When we gaze at the moon on a clear night, we're looking at more than just Earth's faithful companion. We're witnessing the aftermath of the most catastrophic event in our planet's history. Approximately 4.5 billion years ago, a Mars-sized planet called Theia collided with the young Earth, ejecting massive amounts of debris into orbit. This debris eventually coalesced to form the moon we know today. While this theory, known as the giant impact hypothesis, is widely accepted, it leaves several questions unanswered. One of the most intriguing is, what happened to the rest of Theia? Recent scientific discoveries suggest that the answer to this question might lie deep within our planet, potentially solving another long-standing geological mystery in the process. The mystery of the large low-velocity provinces, LLVPs. Deep beneath our feet, nearly 3,000 kilometers underground, lie two enormous blobs of unusually dense material. These structures, each thousands of kilometers across and hundreds of kilometers tall, sit just above the boundary between Earth's mantle and core. One is located beneath the Pacific Ocean, while the other resides under Africa. Intriguingly, both regions are associated with an unusually high number of hotspot volcanoes at the surface, leading geologists to suspect a connection between these deep structures and magma plume formation. Discovering the blobs, seismic tomography. Our knowledge of these deep structures comes from a technique called seismic tomography. This method uses seismic waves from earthquakes to create images of Earth's interior, much like how medical CT scans use X-rays to image the human body. The speed of seismic waves depends on the physical properties of the material they pass through. By analyzing how fast these waves travel and how they reflect and refract through Earth's structure, scientists can construct a picture of our planet's interior. This technique has revealed the various layers of Earth, the crust, mantle, and core, without the need for direct observation. It's also how we discovered the two anomalous blobs deep within the mantle. Characteristics of the LLVPs. Scientists have dubbed these structures large low-velocity provinces, LLVPs, because seismic waves travel through them about 0.5% slower than through the surrounding mantle. This slight decrease in velocity suggests that the LLVPs are composed of material that's different from the rest of the mantle in some way. Key characteristics of the LLVPs include enormous size. Each blob is thousands of kilometers across and hundreds of kilometers tall. Deep location. They sit just above the core mantle boundary, about 3,000 kilometers below the surface. Slower seismic wave velocity. Waves travel about 0.5% slower through these regions. Sharp boundaries. The edges of the LLVPs are surprisingly abrupt. Association with surface phenomena. They correlate with regions of increased hotspot volcanism. Theories about the origin of LLVPs. Since their discovery in the 1980s, scientists have proposed various theories to explain the nature and origin of the LLVPs. Some of the leading hypotheses include temperature difference. The simplest explanation is that the LLVPs are just hotter than the surrounding mantle. However, models of large hot plumes tend to produce thin, narrow structures rather than the wide, spread-out shape of the LLVPs. Cluster of smaller plumes. Another possibility is that the LLVPs are actually clusters of smaller plumes that appear as one large structure in seismic imaging due to resolution limitations. Primordial crust. Some scientists suggest the LLVPs could be remnants of Earth's very first crust, a sort of first draft of our planet's surface. Subducted oceanic plates. A leading theory proposes that the LLVPs are graveyards of ancient oceanic plates that subducted long ago, but haven't fully mixed with the rest of the mantle. However, a 2023 study has proposed a new explanation that ties together the mystery of the LLVPs with the ancient collision that formed the moon. The Theia hypothesis, a new explanation for LLVPs. The new study suggests a radical yet elegant explanation for the LLVPs. They could be remnants of Theia's mantle, left behind after the giant impact that formed the moon. The giant impact and its aftermath. When Theia collided with the proto-Earth, the force was so great that it essentially scrambled the two planets together. Most of the iron from both planets' cores fused to form Earth's current core, while their mantles mixed. Some of this mixture remained on Earth, while some was ejected into orbit, eventually forming the moon. This means that today's moon is composed of a mixture of Earth's original mantle and Theia's mantle, with a greater proportion coming from Theia. Analysis shows that Earth's mantle is about 8% iron oxide, while the Moon's is about 10%. From this, researchers concluded that Theia's mantle likely contained between 13% and 18% iron oxide, making it significantly denser than Earth's mantle. Modeling the post-impact Earth. To test their hypothesis, the researchers created a mathematical model simulating how the material left on Earth would have mixed after the collision. Their model revealed several key insights. Mantle separation. The impact separated Earth's mantle into an upper melted layer and a lower solid layer. Initial mixing. Initially, mantle material from both planets was mixed in the upper layer. Density-driven settling. Over time, the denser, more iron-rich material from Theia solidified and sank into the solid layer of Earth's mantle. Blob formation. This denser material accumulated into large blobs just above the core. Long-term stability. The model showed these blobs could remain stable over billions of years. This scenario provides a compelling explanation for the LLVPs we observe today through seismic tomography. It suggests that these anomalous structures in Earth's deep mantle could actually be chunks of an ancient, disembodied planet. Supporting evidence, volcanic gas ratios. The Theia hypothesis also explains another puzzling observation made by geologists. The ratios of certain trace gases in rocks erupted from hotspot volcanoes are oddly similar to those found in lunar rocks. This similarity makes perfect sense if magma plumes are rising from the LLVPs, composed of Theia's mantle material, before erupting at the surface. In a poetic twist, this means that some volcanic eruptions on Earth could be viewed as the dead planet Theia reaching up from the lower mantle and out through the Earth's surface, billions of years after its demise. Implications in future research. While the Theia hypothesis for the origin of LLVPs is compelling, it's important to note that it doesn't definitively disprove other theories. The debate about the nature and origin of these deep mantle structures is likely to continue. However, this new hypothesis has the appealing feature of potentially solving two long-standing geological mysteries with a single explanation. If confirmed, this theory would have profound implications for our understanding of Earth's formation and evolution. It would mean that we're still feeling the effects of an event that occurred over 4 billion years ago, and that parts of another planet are buried deep within our own. Future research directions might include more detailed seismic imaging of the LLVPs to better understand their structure and composition, geochemical analysis of volcanic rocks from hotspots associated with LLVPs to look for unique signatures that might indicate an origin from Theia, refinement of computer models simulating the giant impact and subsequent mantle dynamics, comparative studies of other terrestrial planets and moons in our solar system to see if similar structures exist elsewhere. Conclusion. The story of Theia and the LLVPs reminds us of the dynamic and violent history of our planet. It illustrates how events from billions of years ago can leave lasting imprints on a planet's structure and evolution. The fact that we can probe these ancient events using modern scientific techniques is a testament to human ingenuity and the power of scientific inquiry. As we continue to unravel the mysteries of Earth's deep interior, we gain not only a better understanding of our planet's past, but also insights into its present and future behavior. The study of LLVPs and their potential link to the moon-forming impact highlights the interconnectedness of planetary processes across vast spans of time and space. Whether or not the Theia hypothesis for LLVPs proves correct, it serves as a powerful reminder of the complex and often surprising ways in which our planet has evolved. It encourages us to look at familiar features, like the moon in the night sky or a volcanic eruption, with fresh eyes, seeing in them the echoes of cosmic events from the dawn of our solar system. As we gaze up at the moon on a quiet evening, we can now appreciate it not just for its serene beauty, but as a celestial monument to one of the most transformative events in Earth's history. And we can wonder at the possibility that remnants of the collision that formed it might still lie buried deep within our planet, influencing geological processes to this day. The search for answers about Earth's deep structure and ancient history continues, driven by human curiosity and enabled by advancing technology. Each new discovery brings us closer to understanding our planet's past, and by extension, its future. In the process, we're reminded of the dynamic, ever-changing nature of the seemingly solid ground beneath our feet.